Hello friends, welcome to this YouTube channel. Today we are going to solve one numerical problem on three-phase induction motors. By solving this problem, we shall learn how to determine overall efficiency and shaft torque of a three-phase induction motor for a particular value of slip when parameters of its exact equivalent circuit are given. A 208-volt 60 Hz 4-pole 3-phase star-connected induction motor is rated at 15 HP. Its per-phase components referred to stator side are R1 equals to 0.22 ohm, R2 dash equals to 0.127 ohm, X1 equals to X2S dash equals to 0.43 ohm, Xm equals to 15 ohm. The rotational losses amount to 500 watts. Using exact equivalent circuit for 5% slip, we have to determine the motor speed, line current, stator copper losses, air gap power, mechanical power developed, induced torque, load torque, and overall efficiency. Let us first write down the given data. For rotor winding, resistance per phase referred to the stator R2 dash equals to 0.127 ohm and standstill leakage reactance per phase X2S dash equals to 0.43 ohm. For a value of slip S, expression for rotor impedance per phase referred to the stator Z2 dash equals to R2 dash by S plus JX2S dash. Given slip S equals to 5%, that is equal to 0.05 per unit. Therefore, Z2 dash equals to 0.127 by 0.05 plus J times 0.43 ohm, that is equal to 2.54 plus J times 0.43 ohm. This may be written in polar form as 2.576 ohm at an angle 9.61 degree. For shunt branch, given magnetizing reactance per phase Xm equals to 15 ohm. Let us now calculate Jxm plus Z2 dash. Using values we get 2.54 plus J times 15.43 ohm. This may be written in polar form as 15.6377 ohm at an angle 80.652 degree. Now we shall determine equivalent impedance per phase. ZDQ equals to Jxm parallel with Z2 dash, that is equal to Jxm into Z2 dash divided by Jxm plus Z2 dash. Using values we get 15 at an angle 90 degree into 2.576 at an angle 9.61 degree divided by 15.6377 at an angle 80.652 degree. That gives us 2.471 ohm at an angle 18.958 degree. Given line-to-line terminal voltage VL equals to 208 volts. For star-connected induction motor, terminal voltage per phase ET equals to VL by root 3, that is equal to 208 divided by root 3, that gives us 120 volts. For stator winding, given resistance per phase R1 equals to 0.22 ohm and leakage reactance per phase X1 equals to 0.43 ohm. Expression for stator impedance per phase Z1 equals to R1 plus Jx1 equals to 0.22 plus J times 0.43 ohm. We have determined equivalent impedance per phase ZEQ equals to 2.471 ohm at an angle 18.958 degree. This may be written in Cartesian form as 2.33697 plus J times 0.80277 ohm. Now we shall compute total input impedance per phase. Zin equals to Z1 plus ZEQ. Using values we get 2.55697 plus J times 1.23277 ohm. This may be written in polar form as 2.83863 ohm at an angle 25.7397 degree. We have obtained total input impedance per phase Zin equals to 2.83863 ohm at an angle 25.7397 degree. Let us now calculate stator current per phase. I1 equals to ET divided by Zin. Taking terminal voltage per phase ET as reference, we get I1 equals to 120 at an angle 0 degree divided by 2.83863 at an angle 25.7397 degree. That gives us 42.2739 ampere at an angle minus 25.7397 degree. Now we shall calculate rotor current per phase referred to the stator. I2 dash equals to JXM divided by JXM plus Z2 dash into I1. Given magnetizing reactance per phase XM equals to 15 ohm. We have determined JXM plus Z2 dash equals to 15.6377 ohm at an angle 80.652 degree. Therefore, I2 dash equals to 15 at an angle 90 degree divided by 15.6377 at an angle 80.652 degree into 42.2739 at an angle minus 25.7397 degree. That gives us 40.55 ampere at an angle minus 16.3917 degree. Expression for air gap power Pg equals to 3 times I2 dash square into R2 dash by S. Given per phase rotor resistance referred to the stator R2 dash equals to 0.127 ohm and slip S equals to 0.05 per unit. Therefore, Pg equals to 3 into 40.55 square into 0.127 by 0.05. That gives us 12,529.585 watt. Now we shall calculate mechanical power developed. Pm equals to 1 minus S times Pg. Using values we get 1 minus 0.05 into 12,529.585, which is approximately equal to 11,903 watts. In polar form we can write stator current per phase I1 equals to I1 at an angle minus phi1 equals to 42.2739 ampere at an angle minus 25.7397 degree. For star connected induction motor, stator current per phase equals to stator line current. Now we shall calculate stator power factor. cos phi 1 equals to cos of 25.7397 degree, that is equal to 0.9008 lagging. Now we shall determine total input power. Pin equals to root 3 times VL into I1 cos phi 1. Using values we get root 3 into 208 into 42.2739 into 0.9008, which is approximately equal to 13,719 watts. Now we shall calculate stator copper loss. PS copper equals to 3 times I1 square into R1, given per phase stator resistance R1 equals to 0.22 ohm. Therefore, PS copper equals to 3 into 42.2739 square into 0.22, which is approximately equal to 1179.4745 watt. Let us now determine total output power. PO equals to PM minus PR, given rotational losses PR equals to 500 watts. We have computed mechanical power developed PM equals to 11,903 watts. Therefore, PO equals to 11,903 minus 500, that gives us 11,403 watts. Now we shall compute overall efficiency of the motor. Eta equals to PO divided by Pin. Using values we get 11,403 divided by 13,719, that gives us 0.8312 per unit or 83.12%. Given number of poles of the machine P equals to 4 and supply frequency F equals to 60 Hz. Let us now calculate synchronous speed. Ns equals to 120 F by P. Using values we get 120 into 60 divided by 4, that gives us 1800 revolutions per minute. Now we shall determine motor speed. Nr equals to 1 minus S times Ns. Given slip S equals to 0.05 per unit, therefore Nr equals to 1 minus 0.05 into 1800, that gives us 1710 revolutions per minute. Now we shall calculate motor speed in radians per second. Omega r equals to 2 pi into nr by 60, that is equal to 2 pi into 1710 by 60, that gives us 179. Expression for induced torque Td equals to Pm divided by omega r. We have computed mechanical power developed Pm equals to 11,903 watts. Therefore, Td equals to 11,903 divided by 179, which is approximately equal to 66.5 Newton meter. Load torque TSH equals to PO divided by omega r. We have obtained total shaft power output PO equals to 11,403 watts. Therefore, TSH equals to 11,403 divided by 179, which is approximately equal to 63.7 Newton meter. Now we shall compute equivalent rotor current I2' using Thevenin's theorem. For this purpose we shall remove the load, that is the equivalent rotor impedance Z2 dash from this circuit. Now, the open circuit voltage as seen from terminals A and B gives us Thevenin's voltage. We have obtained stator impedance per phase Z1 equals to 0.22 plus J times 0.43 ohm. This may be written in polar form as 0.483 ohm at an angle 62.9 degree. Rotor impedance per phase referred to the stator Z2 dash equals to 2.54 plus J times 0.43 ohm, that is equal to 2.576 ohm at an angle 9.61 degree, and shunt impedance per phase Z0 equals to J times Xm, that is equal to J times 15 ohm. This may be written in polar form as 15 ohm at an angle 90 degree. Now we shall compute Z0 plus Z1 using values we get 0.22 plus J times 15.43 ohm. This may be expressed in polar form as 15.43157 ohm at an angle 89.1831 degree. Now we shall calculate Thevenin's voltage. Thevenin equals to Z0 into I, that is equal to Z0 into ET divided by Z0 plus Z1. Using values we get 15 at an angle 90 degree into 120 at an angle 0 degree divided by 15.43157 at an angle 89.1831 degree. That gives us 116.644 volt at an angle 0.8169 degree. To determine Thevenin's impedance, we shall short circuit the voltage source. Now the impedance as seen from terminals A and B gives us Thevenin's impedance. Z Thevenin equals to Z0 parallel with Z1, that is equal to Z0 into Z1 divided by Z0 plus Z1. Using values we get 15 at an angle 90 degree into 0.483 at an angle 62.9 degree divided by 15.43157 at an angle 89.1831 degree. That gives us 0.4695 ohm at an angle 63.7169 degree. This may be written in Cartesian form as 0.2079 plus J times 0.42096 ohm. Let us now calculate Z Thevenin plus Z2 dash. Using values we get 2.7479 plus J times 0.85096 ohm. This may be written in polar form as 2.876645 ohm at an angle 17.2065 degree. We have obtained Thevenin's voltage Thevenin equals to 116.644 volt at an angle 0.8169 degree, and Thevenin's impedance Thevenin equals to 0.4695 ohm at an angle 63.7169 degree. Let us draw the Thevenin's equivalent circuit as seen from terminals A and B. Now we shall connect the load, that is the equivalent rotor impedance per phase Z2 dash back to this circuit. Let us determine the load current, that is the rotor current per phase referred to the stator. I2 dash equals to IL equals to Thevenin divided by Thevenin plus ZL, or Thevenin divided by Thevenin plus Z2 dash. we have computed Z Thevenin plus Z2 dash equals to 2.876645 ohm at an angle 17.2065 degree. Using values we get I2 dash equals to 116.644 at an angle 0.8169 degree divided by 2.876645 at an angle 17.2065 degree. That gives us 40.5486 ampere at an angle minus 16.3896 degree. Now we shall determine induced EMF per phase. E1 equals to Z2 dash into I2 dash. We have obtained rotor impedance per phase referred to the stator Z2 dash equals to 2.576 ohm at an angle 9.61 degree. Therefore, E1 equals to 2.576 at an angle 9.61 degree into 40.5486 at an angle minus 16.3896 degree. That gives us 104.4532 volt at an angle minus 6.7796 degree. We have obtained induced EMF per phase E1 equals to 104.4532 volt at an angle minus 6.7796 degree. This may be written in Cartesian form as 103.723 minus J times 12.33 volt. Let us now calculate stator current per phase. I1 equals to ET minus E1 divided by Z1. We have determined stator impedance per phase. Z1 equals to 0.483 ohm at an angle 62.9 degree. Using values we get I1 equals to 120 minus of 103.723 minus J times 12.33 divided by 0.483 at an angle 62.9 degree. That gives us 20.4198 at an angle 37.1443 degree divided by 0.483 at an angle 62.9 degree. That is equal to 42.277 ampere at an angle minus 25.7557 degree. So today we have solved one numerical problem on three-phase induction motors. By solving this problem, we have learned how to determine overall efficiency and shaft torque of a three-phase induction motor at a particular value of slip when parameters of its exact equivalent circuit are given. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.